Welcome to today's paper reading. Today's paper is titled, Multilingual Large Language Model, a Survey of Resources, Taxonomy and Frontiers. This paper was published on the AR14 preprint by Libo Chen and colleagues from Central South University and Harbin Institute of Technology. This paper addresses the capabilities of multilingual large language models, MLLMs, in handling and responding to queries in multiple languages, achieving significant success in multilingual natural language processing tasks. Despite these advancements, there is a noticeable absence of a comprehensive survey summarizing existing approaches and recent developments in this field. To fill this gap, the authors present a thorough review and provide a unified perspective to summarize the recent progress and emerging trends in MLLMs literature. The key contributions of this paper include conducting the first survey in the MLLMs research field, offering a new taxonomy to summarize the current progress, highlighting several emerging frontiers and discussing the corresponding challenges, and collecting abundant open-source resources such as relevant papers, data corpora, and leaderboards. The authors hope that their work will facilitate quick access to these resources and stimulate further breakthrough research in MLMs. Recent years have seen significant advancements in large language models, LLMs, which have demonstrated outstanding performance on various natural language processing tasks. These models have also shown surprising emergent capabilities such as in-context learning and chain-of-thought reasoning. However, most LLMs are primarily focused on English tasks, making them less effective in multilingual settings, especially in low-resource scenarios. There are over 7,000 languages worldwide, and with globalization, it is crucial for large language models to serve diverse languages. Multilingual large language models, MLMs, are gaining attention for their ability to handle multiple languages. These models can be categorized into two groups based on their alignment strategies, parameter tuning and parameter frozen. Despite the success of MLMs, there is a lack of comprehensive review and analysis in the literature, which this work aims to address. Figure 1 illustrates the difference between parameter tuning alignment and parameter frozen alignment in multilingual large language models, MLMs. In parameter tuning alignment, the model fine-tunes its parameters to achieve cross-lingual alignment, which involves adjusting the model's internal parameters to better handle multiple languages. On the other hand, parameter frozen alignment uses prompts directly for alignment without any parameter tuning, relying on the model's existing capabilities to manage multilingual tasks. Both methods aim to enhance the model's ability to handle and respond to queries in multiple languages, but they approach this goal differently, with one adjusting the model's parameters and the other relying on prompt design. Figure 2 illustrates the evolution of selective multilingual large language models, MLLMs, over the past 5 years. The colored branches in the figure represent different alignment stages. For models that have undergone multiple alignment stages, the final stage is highlighted. This visualization helps to track the advancements and changes in alignment strategies within the MLM landscape. In this section, we formally describe the definitions of monolingual and multilingual large language models. A monolingual large language model, LLM, can only process one language at a time, such as English or Chinese, as defined by the function mono, shi, li. In contrast, a multilingual LLM can handle and produce content in various languages simultaneously, defined by multi, x. Additionally, we categorize the data resources used for these models into three main types: manual creation, web crawling, and benchmark adaptation. These resources are essential for both multilingual pre-training and supervised fine-tuning, SFT, data, which are further divided into classes such as manual creation, machine translation, benchmark adaptation, and MLLMs-aided generation. Figure 3 illustrates the distinction between monolingual large language models, LLM, and multilingual large language models, MLM. Monolingual LLMs, as depicted in Part A, are designed to process and generate content in a single language, such as English or Chinese. The process can be formally defined where the model generates output in the intended language or indicates an unexpected language if the input is not in the designated language. In contrast, multilingual LLMs, shown in Part B, are capable of handling and producing content in multiple languages simultaneously. The formal definition for MLLM shows that the model's response can belong to multiple languages, highlighting its ability to manage diverse linguistic inputs and outputs. In this section, we discuss the data resources used in the stages of multilingual large language model training. For pre-training, models such as GPT-3, MT5, and ERNIE 3.0 are utilized. In the supervised fine-tuning stage, resources include FLAMPLM, TK-Instruct, and MT0. For reinforcement learning from human feedback, models like GPT 3.5, ChatGLM, and GPT-4 are employed. Detailed statistics of these data resources can be found in the appendix. Figure 4 presents a taxonomy of multilingual large language models, MLLMs, categorizing them into parameter tuning alignment methodology and parameter frozen alignment methodology. The parameter tuning alignment methodology involves progressively advanced training strategies to refine model parameters for better cross-lingual performance. In contrast, the parameter frozen alignment methodology employs 4 prompting strategies: direct prompting, code switching prompting, translation alignment prompting, and retrieval augmented alignment, while keeping the original model parameters unchanged. The taxonomy presented in this section categorizes alignment strategies into 2 main types: parameter tuning alignment, PTA, and parameter frozen alignment, PFA. PTA involves progressively advanced training strategies such as pre-training alignment, supervised fine-tuning, SFT, alignment, and reinforcement learning from human feedback, RLHF, alignment. These stages aim to refine model parameters for systematic multilingual performance. On the other hand, PFA focuses on prompting strategies without parameter tuning, including direct prompting, code switching prompting, and translation alignment prompting. Additionally, the downstream fine-tuning stage includes full parameter fine-tuning and parameter-efficient fine-tuning approaches, as well as retrieval augmented alignment to enhance model performance. Figure 5 provides an overview of the parameter tuning alignment, PTA, methods, detailing the progression from the pre-training stage to the downstream fine-tuning stage. Each stage incorporates multilingual data to enhance cross-lingual alignment. Notably, the figure highlights the use of parameter-efficient fine-tuning, PFT, and low-rank adaptation, LoRa, to optimize efficiency in the alignment process. Figure 6 provides an overview of the parameter-frozen alignment methods discussed in Section 4.2. These methods include direct prompting, which involves directly outputting the request without additional instructions for implicit alignment through MLLM itself. Code switching prompting integrates multilingual words into a single language utterance, a typical language phenomenon for effective language alignment. Translation alignment prompting translates the query into other languages for better alignment, which can be divided into key information translation, direct translation, step-by-step translation, and restatement. These strategies aim to perform alignment without parameter tuning, leveraging prompting strategies to elicit the alignment potential of MLLMs. In the future work of multilingual large language models, MLLMs, several key areas need further exploration. Firstly, hallucination issues in MLLMs, where models generate incorrect or misleading information, require advancements in multilingual hallucination detection and alleviation strategies. This includes improving methods during pre-training and decoding stages. Secondly, knowledge editing in MLLMs is crucial for maintaining accurate and up-to-date information across languages. Challenges here include continuous integration of new knowledge and balancing universal knowledge with language-specific details. Lastly, ensuring safety and fairness in MLLMs involves addressing the lack of safety benchmarks, filtering out unsafe data, and improving performance and token costs for low-resource languages. In this work, the authors present a comprehensive survey of advancements in multilingual large language models, MLLMs. They introduce a new taxonomy from alignment perspectives, which provides a unified view for researchers to understand the progress of MLLMs. Additionally, the authors highlight emerging trends and their associated challenges in MLLMs, aiming to facilitate further research and inspire more breakthroughs in the MLLMs literature. Thank you for watching.